Right now, in this exact moment, astronomers are staring at data they genuinely cannot explain. Not because they lack the tools or the intelligence, but because what those tools are showing them shouldn't actually exist, at least not yet, not by billions of years. And the worst part, the part that keeps cosmologists awake at night, is that this isn't some fringe discovery from a single questionable observation. This is the James Webb Space Telescope, humanity's most powerful eye on the universe, working in perfect harmony with NASA's Chandra X-ray Observatory, both of them pointing at the same patch of sky and screaming the same impossible message. The universe assembled itself far faster than we ever thought possible. Let me show you why this discovery matters so much and why it's forcing scientists to seriously consider that nearly everything we've believed about how the cosmos builds itself might need a fundamental rethinking. The story actually begins not with a discovery, but with a crisis. For decades, cosmologists have built incredibly detailed computer models of how the universe evolved. These models start from the moment right after the Big Bang, from measurements so precise they come from studying the cosmic microwave background, that ancient light still traveling through space from the universe's childhood. Using those measurements as a foundation, scientists then run simulations watching billions of virtual years pass in seconds, modeling how gravity slowly pulled matter together, how the first stars ignited, how galaxies formed around those stars, and eventually, how galaxies began clustering together under mutual gravitational attraction. These models are predictions, essentially prophecies about what we should find when we look deep enough into space and therefore deep enough back in time. And for years, they worked beautifully. They predicted what we would find, and then we found it. The agreement between theory and observation gave us confidence that we understood the universe. But then James Webb launched. The moment Webb opened its infrared eyes in 2022, something unexpected started happening. Again and again, the telescope found galaxies in the early universe that shouldn't exist yet, according to these carefully constructed models. Galaxies that were too big, too bright, too chemically mature, galaxies that had no business being so well developed when the universe was only a few 100 million years old. One particularly infamous example was a galaxy so massive, so chemically complex, that astronomers struggled to explain how the universe could have built something of that scale in such a short time. Each discovery was a small alarm bell, a minor discrepancy that astronomers tried to explain away. Perhaps their calculations were slightly off. Perhaps the models needed minor adjustments. Perhaps the universe operated differently in specific regions. But then the discoveries kept coming, each one larger and stranger than the last, each one forcing astronomers to add more and more caveats to their understanding, until astronomers began to wonder if this wasn't a series of minor problems, but a fundamental misconception about how quickly the early universe could organize itself. This is the context in which a team of astronomers, led by Akos Bogdan at the Center for Astrophysics, turned both Webb and Chandra toward a region of sky called the Chandra Deep Field South. This patch of sky already held the distinction of being one of the most intensely studied regions in existence. Chandra had stared at it for years, accumulating the deepest X-ray observations the observatory had ever collected. Webb had examined it with its infrared instruments, cataloging galaxies at impossible distances. The astronomers weren't necessarily expecting to find anything revolutionary. But they were patient, they were systematic, and sometimes that's exactly when the universe decides to reveal its secrets. What Webb's infrared instruments detected was a cluster of galaxies unlike anything they'd seen before. At least 66 separate galaxies crowded impossibly close together, all appearing to sit at roughly the same distance from Earth, all held in place by their mutual gravitational attraction. This wouldn't have been entirely shocking on its own. Astronomers find clusters of galaxies all the time. But here's where the timeline becomes the problem. Based on how far this light had to travel to reach us, based on the redshift of the light itself stretched into infrared wavelengths by the expanding universe, these galaxies existed when the universe itself was barely 1 billion years old. Think about that for a moment. The universe is currently 13.8 billion years old. These galaxies assembled into a bound cluster structure, all orbiting together, when the universe was barely 7% of its current age. Now, you might be thinking, so what? Why should age matter if gravity can pull things together? The answer requires understanding what a protocluster actually is and why they take so long to form. A protocluster is a galaxy cluster in its earliest, most chaotic stage of formation. It's not like you can just have galaxies sitting near each other and call it a cluster. For a genuine cluster to exist, these galaxies must be bound together, caught in each other's gravity, forming a unified system. But before they settle into this bound state, the surrounding gas must be pulled inward by that same gravity, compressed and heated by shock waves from infalling material until it reaches temperatures of tens of millions of degrees. At those temperatures, the gas becomes plasma, and plasma at those energies glows brilliantly in X-rays. Building this structure requires time. It requires enough galaxies to have already formed. It requires those galaxies to be dense enough that gravity can actually catch and bind them together. It requires all that gas to fall inward, compress, and heat up. According to every computer model astronomers have run, every simulation that matches our observations of the nearby universe, this process should take at least 2 to 3 billion years. JD's ID1 appears to have accomplished it in about 1 billion years. This is where Chandra enters the story as more than just a supporting player, but as the crucial confirming voice that transforms an interesting observation into a genuine scientific anomaly. Chandra's entire purpose is to detect X-rays from the hottest, most energetic material in the cosmos. When the research team pointed Chandra at the same patch of sky where Webb had found those 66 galaxies, the X-ray telescope picked up a clear, unmistakable signal. A massive cloud of superheated gas surrounding those galaxies, glowing brilliantly in X-rays, exactly what you'd expect to see if gravity had been actively pulling material inward and heating it to extreme temperatures. This wasn't a coincidence. This wasn't Webb finding galaxies that just happened to line up behind some other structure. This was confirmation that all 66 of those galaxies were gravitationally bound together inside a shared envelope of hot gas. This was a real, physical, genuinely formed protocluster sitting 12.7 billion light years away from Earth. Let me pause here and make sure you understand why finding both of these pieces together matters so much. Webb alone could have identified the galaxies, but galaxies can be deceiving. Sometimes, objects that look close together from our perspective on Earth are actually scattered across vast distances, just lining up along our line of sight by pure chance. A single photograph might show hundreds of galaxies clustered in a small region, but spectroscopic measurements revealing their redshifts might show they're actually spread across billions of light years of space. Chandra alone could have found hot gas, but hot gas clouds exist in many places throughout the universe, and attributing a particular cloud to a particular group of galaxies requires confirmation from independent evidence. But when both telescopes see the same thing in the same location at the same distance in cosmic time, when the X-ray glow surrounds exactly where the galaxies are, when the redshift measurements all agree on the same distance, when the physics all checks out perfectly, that's when astronomers can be confident they found something real. This multi-wavelength approach, combining infrared observations from Webb with X-ray observations from Chandra, represents modern astronomy at its finest, using complementary instruments to answer questions neither could fully resolve alone. To understand what happens next, you need to understand what makes galaxies clusters so valuable to cosmology in the first place. Galaxy clusters are the largest gravitationally bound structures in the entire universe. They contain anywhere from a few hundred to several thousand individual galaxies, all held together not just by their mutual gravity, but largely by something invisible called dark matter. Dark matter is one of the great mysteries of cosmology. It makes up roughly a quarter of everything that exists, and yet we've never directly detected it. We know it's there because of its gravitational effects. The galaxies and clusters move too fast. The clusters would fly apart if the only gravity holding them together was the gravity from the galaxies themselves. Something invisible is adding mass and gravity to these structures. That something is dark matter. Scientists estimate that for every single unit of ordinary matter in a galaxy cluster, there's roughly 5 to 6 units of dark matter, providing additional gravitational attraction. This invisible scaffolding is absolutely essential to understanding how clusters form and maintain their cohesion over billions of years. Surrounding all the galaxies in a mature cluster is an enormous pool of superheated gas, sometimes reaching temperatures of tens of millions of degrees. This gas is so hot that atoms have been stripped of their electrons, creating what physicists call plasma. In clusters like these, this plasma glows brilliantly in X-rays. When you observe a galaxy cluster, you're seeing 3 things simultaneously: the galaxies themselves, the dark matter revealed through its gravitational effects, and the hot gas revealed through its X-ray emissions. Each one tells you something different about how the universe evolved. And scientists use clusters as some of the most valuable tools available for understanding cosmology because of this. They're so massive that they bend light through something called gravitational lensing, acting like natural magnifying glasses that help us see even more distant objects behind them. They take so long to form that their very existence tells us something profound about how quickly the universe can assemble complex structures. They're shaped by the balance between dark matter, dark energy, ordinary matter, and gravity itself, making them perfect test cases for cosmological theory. This is precisely why JD's ID1 represents such a genuine crisis for cosmology. Computer simulations of the early universe, simulations that match our observations of galaxy clusters close to us, consistently show that building something as massive and organized as JD's ID1 requires somewhere between 2 and 3 billion years. The raw material needs time to accumulate. The dark matter needs time to clump into large structures. The ordinary matter needs time to collect and condense around those dark matter scaffolds. Gravity works constantly, but it works slowly when you're trying to assemble something as enormous as a galaxy cluster from the nearly uniform soup of matter that existed in the early universe. Theoretical physicists didn't arbitrarily pick 2 to 3 billion years as the expected formation time. That number emerged from detailed simulations based on real physics, based on everything we understand about how gravity operates and how quickly matter can condense under its influence. Jati's ID1 appears to have formed in roughly 1 billion years. That's not just early, that's impossibly early. That's like watching a forest grow to full maturity in a matter of months, when every tree species you know requires decades to reach that size. Someone would be frantically checking their equipment and their calculations, wondering where the mistake must be. But here's the thing. There doesn't appear to be a mistake. The research team has checked and rechecked their work. Webb's infrared measurements of those 66 galaxies all point to the same distance from Earth. The redshift measurements all confirm they're at the same cosmic epoch. Chandra's X-ray data all shows a coherent cloud of hot gas surrounding them. Multiple teams of scientists have examined this data. The discovery was published in the prestigious journal Nature in January 2026. This isn't some fringe claim or preliminary result. This is real astronomy from real telescopes, verified and cross-checked multiple times. What makes this discovery even more significant is that it's not alone. Webb's deep survey of the same sky field known as JADIS has identified 5 other protocluster candidates that look similar. They're all at enormous distances, all from the early universe, all appearing to be clusters of galaxies grouped together. Jati's ID1 stands out because it's the only one where Chandra could confirm the presence of the hot gas signature. The other 5 remain candidates, intriguing but unconfirmed, waiting for either more observation time or stronger evidence that they're genuine gravitationally bound structures rather than chance alignments of galaxies that happen to sit near each other along our line of sight. To really appreciate what makes this discovery significant, you need to understand something about the nature of cosmological models. These models aren't just interesting academic exercises, they're the foundation of essentially everything we think we understand about the universe's history. They start from the Big Bang and trace the universe's evolution forward to the present day. They describe how the first stars formed from the primordial gas clouds, how those stars exploded at the end of their lives and scattered heavy elements throughout space, how those heavy elements became part of new stars, new planets, eventually the atoms that make up your body. The universe didn't randomly assemble itself into galaxies and clusters. The process was gradual and driven by physics. Every step has been modeled, simulated, and compared against observations. The problem is that JD's ID1 breaks this timeline in a way that's difficult to dismiss as a measurement error or an anomaly. If just one early galaxy is unexpectedly large, maybe that galaxy is unusual. Maybe it formed through some rare process that doesn't usually happen. But when you're finding multiple massive galaxies and entire galaxy clusters in the early universe, all appearing earlier than predicted, you're not looking at statistical fluctuations anymore. You're looking at a pattern that suggests something fundamental about early galaxy and cluster formation needs revision. There are several possible explanations being discussed among astronomers right now, and each one has different implications for how we understand the universe. The first possibility is that galaxy formation in the very early universe was more efficient than current models predict. Perhaps the raw materials for building galaxies, the gas and dust and primordial elements, came together more quickly and were converted into stars with greater efficiency than computer simulations assume. This would mean that the first stars formed more rapidly, exploded and distributed heavy elements more quickly, and allowed subsequent generations of stars to form sooner. This would mean that galaxies formed faster, giving them more time to accumulate enough galaxies for a protocluster to form. The second possibility is that dark matter clumped into large structures earlier in cosmic history than existing simulations predict. The dark matter is the gravitational scaffold that galaxies form around. According to current theory, dark matter doesn't form stars or emit light. It simply sits there, providing gravitational attraction. If that scaffold existed earlier, then galaxies would have had more gravitational structure to coalesce around, potentially allowing clusters to assemble faster. This would imply that dark matter physics operates differently than currently modeled, or that dark matter was distributed differently in the early universe than expected. The third possibility is that this particular region of the early universe was simply an unusually dense pocket of matter, a rare statistical outlier, a cosmic anomaly rather than evidence of a universal pattern. In this scenario, JDA's ID1 would be remarkable but not typical, a region where gravity happened to work faster than average because matter was more concentrated than usual. Right now, in this moment, with only one confirmed example, astronomers cannot definitively say for certain which explanation is correct. But that uncertainty is precisely what makes this discovery so important. Science advances when observation contradicts prediction. When you find something that doesn't fit into your existing model, that's when you have to look more carefully, question your assumptions, and refine your understanding. JD's ID1 is exactly that kind of discovery. Consider the scale of what JD's ID1 contains to really grasp the magnitude of this mystery. Astronomers estimate its total mass at about 20 trillion times the mass of the Sun. 20 trillion solar masses of material, already gathered together, already gravitationally bound, already organized into a cluster structure in an object that formed within the first billion years after the Big Bang. To put this in perspective, the Milky Way galaxy, our home, the galaxy that contains Earth and the Sun and roughly 1 to 400 billion stars, has a total mass of somewhere between 1 and 1.5 trillion solar masses, including its own dark matter halo. That means JD's ID1, while still only a protocluster and not yet a fully mature galaxy cluster, already contains somewhere around 15 to 20 times the total mass of our entire galaxy. Our galaxy has had 13 billion years to accumulate that much material and structure. JD's ID1 accumulated 15 to 20 times that mass in roughly 1 billion years. When you contemplate numbers like these, the impossibility of it becomes visceral. It's not just that the timescale is shorter than expected. It's that the amount of material organized in that time frame is so enormous that the violation of expectations becomes almost absurd. And yet there it sits in the data from 2 of humanity's most powerful telescopes, confirmed by multiple teams of researchers, published in a leading scientific journal. The discovery process itself reveals something interesting about modern astronomy. Both instruments were pushed to their absolute observational limits to detect this structure. Webb needed to be sensitive enough to pick out 66 individual, extremely faint, extremely distant galaxies crowded closely together. Each one appeared as barely more than a faint smudge of infrared light after traveling for well over 12 billion years across an expanding universe. Chandra needed to detect X-ray emissions so faint coming from gas so far away that it required some of the deepest X-ray exposure time ever collected by the observatory. The researchers essentially stared at this single patch of sky for an extraordinarily long cumulative period, layering exposure upon exposure over an extended stretch of observing time just to gather enough X-ray photons to produce a statistically reliable detection. Neither telescope was simply glancing at this region. Both were staring for an extraordinarily long time at the very edge of their technical capabilities. This brings up an important point about the future of discoveries like this. As powerful as Webb and Chandra are, they're not infinitely sensitive. There are limits to what they can detect. There are regions of space and distant epochs of cosmic time that remain outside their reach. Future telescopes will be even more powerful. NASA is developing instruments that will make Webb look primitive by comparison. The European Extremely Large Telescope, currently under construction, will have a mirror so massive that it will dwarf Webb's already enormous sensors. The Roman Space Telescope, planned for launch in the coming years, will map vast regions of the sky with sensitivity comparable to or exceeding Webb's capabilities. When these instruments come online, astronomers plan to conduct systematic surveys looking for more examples of early galaxy clusters and protoclusters. The Roman Space Telescope alone is expected to map hundreds of millions of galaxies, providing unprecedented statistics about early galaxy populations and their clustering. If astronomers discover not just one confirmed protocluster at 1 billion years after the Big Bang, but 5, 10, or dozens of them scattered across different regions of the sky, that would strongly suggest that rapid cluster formation in the early universe is not a rare anomaly, but a characteristic feature of how the cosmos actually evolved. Multiple independent discoveries of similar structures at similar distances would constitute genuine proof that something fundamental in the standard model needs revision. The statistical weight of multiple observations would be nearly impossible to dismiss or explain away as measurement error or selection bias. The implications of this would be profound. It would mean that the computer models scientists have relied on for decades, models that have shaped our entire understanding of cosmic evolution, require significant revision. It would mean that matter organized itself into large structures far more quickly than theory predicted. It would require cosmologists to reconsider fundamental assumptions about dark matter, about galaxy formation, about the initial distribution of matter in the early universe. A single discovery, however striking, is not enough to rewrite decades of theoretical work. But one confirmed example, with 5 other candidate examples waiting for confirmation, is the beginning of a potential revolution in cosmological thinking. Conversely, if JD's ID1 turns out to be a rare outlier, a unique cosmic accident that doesn't repeat, that would also tell astronomers something valuable. It would suggest that the early universe was far more clumpy and uneven in its distribution of matter than previously thought. Some regions could accumulate enough material quickly enough to form clusters, while other regions remained sparse. This would paint a picture of the early universe as far more heterogeneous, far more varied from place to place, than the relatively smooth and uniform cosmos suggested by current models. Either way, whether JD's ID1 represents a fundamental revision to our understanding of galaxy formation or a fascinating outlier that reveals how much variation existed in the early universe, the discovery represents a genuine turning point in astronomy. This is exactly the type of observation that eventually forces paradigm shifts in science. It's a data point that refuses to fit neatly into existing theory, and those are the discoveries that drive progress. They're also terrifying for scientists whose careers have been built on understanding those older theories, but they're also exhilarating because they represent genuine frontier science, the moment when observation overtakes prediction and forces a rethinking of fundamental assumptions. What happens next will determine whether this discovery reshapes cosmology or remains a curious anomaly. Astronomers are planning to dedicate significant observing time on both Webb and Chandra to examining similar fields of sky, looking for more protoclusters at early cosmic epochs. They're examining the data from the broader JADIS survey more carefully, trying to understand what distinguishes JADIS ID1 from the other candidate protoclusters that haven't been confirmed. They're running new computer simulations, adjusting parameters to see if they can find scenarios where rapid cluster formation in the early universe becomes possible. They're publishing papers, debating interpretations, questioning whether their previous models might have missed something fundamental. Eventually, over billions of years of cosmic time, JADIS ID1 will continue growing. It will pull in more surrounding galaxies and gas, slowly settling into the large, mature galaxy cluster that astronomers observe closer to Earth today. The same structures, containing hundreds or thousands of galaxies bound together by gravity and dark matter, immersed in enormous glowing clouds of superheated gas reaching tens of millions of degrees. JADIS ID1 is a snapshot of what the Milky Way's future might look like if it merged with thousands of other galaxies and collapsed into a massive cluster. It's a glimpse of one possible endpoint of gravitational assembly. It's worth being entirely clear about what this discovery is not, because there's a critical difference between something being scientifically surprising and something being scientifically impossible. JADIS ID1 does not violate any fundamental law of physics. Gravity still works exactly the way Newton and Einstein described it, pulling matter together over time exactly as predicted. Gas still heats up and glows in X-rays exactly the way physics predicts, following the same basic thermodynamics that apply to hot gas anywhere in the universe. The laws of physics haven't been broken. The only thing that's broken is the timeline. JADIS ID1 appears to have organized itself into a gravitationally bound structure faster than current models predict is possible. That's surprising. It's anomalous. It demands explanation, but it's not physically impossible in any sense that violates known physics. This distinction matters profoundly because it's the critical difference between genuine science and pure sensationalism. A discovery that merely contradicts existing expectations, even contradicts them severely, is still potentially explainable within the framework of physics as we understand it. Perhaps some parameter in the models was wrong. Perhaps some process was more efficient than expected. Perhaps the early universe had properties we haven't fully accounted for. These are all questions that science can explore and answer through careful observation and theoretical work. But claiming that JADIS ID1 breaks physics entirely, that it violates fundamental laws and thus suggests something artificial or supernatural, would be claiming far more than the data supports. The real story here is humbler but more profound. It's the story of human knowledge confronting its limits. We built the best models we could based on our understanding of physics and observation. We launched the most powerful telescopes ever created into space. We pointed them at the distant universe and began asking it questions. And the universe, for the first time in a long while, gave us an answer we genuinely weren't expecting. This is science at its best, not settled and comfortable, but confused and challenged and forced to reconsider its deepest assumptions. This is how we learn. This is how understanding advances. Over the coming years, astronomers will continue searching this same patch of sky and others like it, hoping to find more examples of protoclusters at similarly early points in cosmic history. Every observation, whether it confirms more early clusters or fails to find them, will provide information that helps narrow down the possible explanations. Every data point will either strengthen the case that rapid cluster formation is common in the early universe, or build the case that JADIS ID1 is a rare anomaly. The models will be refined, the simulations will be rerun with adjusted parameters, the theories will be debated, and eventually, perhaps over the course of many years, astronomers will reach a new consensus about how the universe actually evolved, a consensus grounded in observations like JADIS ID1 that refuse to fit the old models. This discovery is a reminder that even with instruments as advanced as the James Webb Space Telescope and the Chandra X-ray Observatory, even with centuries of accumulated knowledge about physics and the universe, even with the most brilliant minds in astronomy dedicated to understanding the cosmos, the The universe still has surprises waiting in its earliest chapters. It still has secrets buried in the light of distant galaxies, waiting for the right combination of telescopes, technology, patience, and vision to finally notice what's actually there. And when that moment comes, when the universe finally shows us something that breaks our models and forces us to reconsider everything, that's when science gets genuinely interesting. That's when the real work of understanding begins.